All right, let's go further to finish chapter 5 today. Actually, you can see in last week I showed you this. If you would like to have a huge contact or via, you will see, oh, wait a minute. Thank you. Okay, anyway. You will see from the top to the bottom, the height, the thickness will be much more than the other pattern. You have the smallest but multiple of the vias to reduce the variation in thickness or height. This is much better for high frequency conduction, and it is usually or always the requirement for current processes. Maybe for the newest, just like 7 or 5 nanometers, maybe they would require you not to have such kind of square layout. To my memory, some of them were a bit rectangular, but still the same. You need to use the smallest pattern as many as possible. That is the fundamental requirement. So for example here, we have the polygate source and drain area, and then we have a lot of contacts, right? That is the fundamental requirement. And according to the parasitics, you can see 4 of them will be connected in parallel. It means the resistance will be reduced substantially, okay? And the other issue is, if you would like to get the smallest, the transistor with smallest area, how can you do the layout? Many of the time, you may guess from the very beginning, I simply use the shortest length and the smallest width, okay? Will it generate the smallest area for your layout? No, usually not. Maybe in the past it is the case, but right now, or maybe more than 10 or 20 years ago, it never was this case, because you can see with such kind of smallest W and L, you need to have such kind of dog bone layout. All right? According to the design rules, yeah. If you have the smallest one, then you need to push your way your source or drain from the polygate. So, how can you make the smallest area? Actually, this one. Okay? L could be the minimum, but how about W? No, never. Yeah. According to the minimum requirement, yeah, you have the contact. And I explained already, you need to have the minimum enclosure or the so-called expansion, okay? The top or the bottom layer needs to be larger than the contact or the via itself, right? So with such kind of extension, you will see that is the minimum requirement, all right? So in brief, L could be the minimum, but W, never. All right. In this way, you can compose the minimum area layout. And you can see W larger than the feature size. According to W over L, it can generate more current than this one, right? So usually we don't pursue the, how can I say, the minimum W and L. It doesn't make any sense because it wastes in area, it is larger. It wastes your money. And according to W over L, I mean current driving capability, it is not so good as this one. All right? Keep this in mind. then we can go further. On this page, I would like to highlight a legend, 一个传说。Okay, what kind of legend? Donut layout or ring transistor 环形电晶体 is the best for high frequency operation. But it is not true. Okay, I told you it is only a legend. But why? Okay, it is not partially. How can I say? It is partially true, but partially wrong. Okay. Anyway, allow me to tell you some of the truths. From the very beginning, you can see that is the stacked layout. For a single transistor, you can cut a very wide transistor into half, into 4 pieces, into multiple pieces, then stack the layout. For what? Actually, to reduce not only the area, but also the parasitics. This is what I would like to share the first here. Okay, so you can see the red lines for gate and the blue lines or the green area for source or drain. Alright, so you can see source and drain for regular transistor, actually they are swappable. You can change, you can replace drain with source or replace source with drain as you like. Alright, but according to the layout here, the drain is at this side, source at the other side. Okay, if you swap it to make this become drain, that becomes source, which one is better or the same? Any idea? According to the layout on the screen, which one is better? Or the performance is the same? Never, right? But which one is better? The current pattern is better. Then you swap it. Okay? But why? Okay. Allow me to show you this. The 3-dimensional structure of our MOSFET. I told you already. Where is channel? Below the gate. Okay? Gate oxide, then beneath it is the channel. Alright? And for our circuit, usually the channel is on. For some cases it is off, but usually it is on. Okay? But how much on? I have no idea. Partially on or fully on, I have no idea. Okay, but only for some cases, for few cases, it is off. Most of the time, especially for analog ones, usually it is on, partially on or fully on, blah, blah, blah. When it is on, it means what? You need to raise the, for MOS, for example, MOS, you need to raise the voltage for the gate to attract a lot of carriers to connect your source and drain. To connect, that is the key point. To connect means what? If you have a look at this area, for MOS, out of it, it is P minus. Inside the area, it is M plus. So you have PN junction to surround the whole area, right? Right? And what you have for PN junction? Parasitic capacitance, more specifically. So it means what? You need to face a lot of parasitics at this side wall, 侧墙, this side wall, and the bottom plate. Okay. However, for the other side wall, close to the gate, you don't have PN junction. Why? I told you already. To raise the gate voltage to connect source and drain. Alright? So here it is M plus after strong inversion, actually the channel is also N plus. Alright? No PN junction at all. So it means the side wall just beside the gate actually has much less parasitic capacitance. That is the key point. Okay? So how to reduce the parasitic? Try to make all the side wall just beside the gate. 想尽各种办法把你的侧墙都跟 gate 连在一起。Okay, that is the power of stacked layout. You can see, for example, this area. For this area, right? Both long sides to the left or to the right, they are covered by this polygate, by that polygate. Bingo! With very few parasitic capacitance. Okay? So the only trouble is where? The short sides. Here and there. In this way, stacked layout help us to reduce the parasitic, especially parasitic capacitance. Okay? If you have a look at this one or that one, you have three side wall, just like this, and that, right? With large parasitic capacitance. But the inner one with much less parasitics. That's it. Okay? Got it? Alright. So, to make it even better, this is the donut layout, square layout, or we call it ring transistor. Okay? With such kind of ring layout, you can see inside. For four side walls, they all besides the polygate, right? So the parasitic inside the donut actually is the minimum, and this is the legend. With such kind of minimum parasitic capacitance, those transistors can operate at the highest frequency. Is it true? Usually not. Okay? Because I told you already, it is only a legend. And why? But why? Because everybody told you the same story? Sorry for that. I'm not everybody. I'm different from them. Allow me to show you this one. Keep this in mind. Our chip actually is three-dimensional. It is not flat. No. It has different levels. Okay, so you can see, I'm afraid of what? This one. The parasitic. But even though you try your very best for this area, or that area, you try your very best to reduce the parasitic here. Okay? The inner one, Chen. But you can still see what? How to connect the inner areas. You need metal 9. You need contact. So what will go wrong? Here. The overlap of the connection metal 9 with your polygate. Just like here. For example, this metal 9. Okay, I show you. It is above the gate, right? But very close to the gate. So the parasitic capacitance here is awful. It's quite large. Okay, so you try your very best to reduce the parasitic here, but increase the parasitic there very much. It is even larger than the amount you reduced. So, sorry for that. The overall parasitic is still larger than this one. Alright, so don't try it. don't try it. If you would like to increase the operation frequency, usually, not always, usually focus on stack layout. But for some case, you can apply this to achieve even better, even higher operation frequency. But what cases you can apply? Okay, very simple. According to what I explained already, if you can reduce the parasitic here, you can make it to achieve much higher operation frequency. Okay? So to reduce it means what? You need to push it upward. Right? Don't use metal one for connection. But you can see if I am here and the next device is there, from the beginning we can be connected by metal one. Right? You try to reduce the gate parasitic. So you do such kind of very silly connection. Oh, to the top, then go back to connect your neighbor. It doesn't make any sense. Yes, in this way you can reduce your parasitic capacitance, but you will increase the parasitic resistance very, very much. According to time constant, actually it equals R by C, right? You reduce this, but increase that very much. It doesn't deserve. 这是一个愚蠢的 idea. Okay, that is a silly idea. So what you can do? What is the condition you can apply such kind of ring transistor layout? Unless the next is not here, it is there, to the top. Okay, far away, at least far away from the previous device. Okay? So what is that device far away? From the first floor, inductor. If you would like to connect this device on the first floor to the top layer, it makes a lot of sense. Okay, for example, LNA. Usually you have low noise amplifier, you have inductor, then you have transistor. Oh, bingo. That is what I want to share with you. Transistor on the floor, at the floor, right? But inductor to the top layer. They are far away. So in this way, for this metal wire, it can be from the metal 1, metal 2, all the way to top metal. Then go to connect the inductor. Got it? That's it. Okay? So for cross-sectional view, that is the device. So you use contact metal 1, contact the metal 2, via metal 2, via metal 3, all the way to top metal. Then connect to your inductor. Oh, it makes a lot of sense. Bingo. And this is the reason why I told you this is usually a legend. If you try to increase, try to raise the operation frequency, don't touch it. Unless, again, the next device is far away. I mean, far away from the gate. Okay? Yeah. That's it. Finally, let's go back here. Why? Don't swap it to become source and drain. Why? Allow me to show you this. Again, the metal 9 to connect all those regions in parallel, it has some kind of overlap, with the gate. And again, you have such kind of huge parasitic capacitance. It doesn't make any sense. Okay? So usually, not always, sorry for that. Usually, drain here is better than drain there. Okay? But it is not always. So for any case, we can swap it. Okay. It depends on which is the output node, drain or source? Okay, can you use gate as the output node? No, because gate has not any kind of driving capability. It is isolated from all the others. Okay, so gate definitely can only be input or reference. It never be output. The output for the transistor needs to be drain or source. All right, so allow me to have 100% correct statement for all of you. 100%正确的讲法是什么？ This is for output. It has no overlap with the gate. That's it. Okay? And usually drain is the output, but sometimes source is the output instead. For example, source follower, right? What you learned already from microelectronics, this is the input from the gate, then you have output node from the source instead of drain. Then you need to change it to be the source to reduce the parasitic here. Okay? Yeah. But you may be curious, hey, how about the parasitic there if I am there just like here, right? I will get more parasitic capacitance. No worry. This is the common node, right? Input here, output is there. We try to reduce the parasitic between your input and output. Why? According to Miller effect. Got it? According to Miller effect, the capacitance between input and output will be amplified a lot by this factor. Got it? So the more voltage gain, the larger input capacitance you need to face according to Miller effect. And this is the reason why I told you this is only for output, because it with much less parasitic capacitance. Why? Because it has no overlap here. All right? That's it. So you need to know everything in detail. Don't simply copy and paste what you learn from your teachers, from the textbook, or even from the papers. No. You need to get full understanding, then make the final decision what to do. 见山不是山，见树不是树，一定要搞清楚它的因果关系。Okay, let's go further. I spent too much time for that page, so allow me to speed up my teaching. How to do the layout for a very wide digital transistor. Why we call it digital? Because for analog, we never try it. Why? Okay. You can see this is for source, that is for drain. Okay. So for such kind of serpentine 大蛇状 layout, you have very long interface. From here, all the way, right? Such kind of very long interface between source and drain. The interface between source and drain means the width, right? And the distance between source and drain, that is length. Okay? So, what is the length? Here, that is the length in theory. And what is the width? As I show you, so very wide. Okay? But what is the problem with such kind of layout? Because I call it for digital transistor instead of analog. Simply because it has too few contacts here or there. Got it? So for the others, for example, the carriers needs to go through all the way to this point. It needs to face a lot of parasitic resistance. It doesn't make any sense for analog layout. But why? Digital circuit can use it because without so many contacts, you can reduce the overall area. That's it. Okay? If you would like to reduce the overall area, you can apply, but it never be good for analog layout. Anyway, I wouldn't like to recommend you to do such kind of CD layout. Forget about it. Let's go further. It will make much more sense. You still have the serpentine, right? For your gate. The W is also very large. Alright? So it is similar to that. However, we have as many contacts here or there as possible. I mean for source and drain. We have as many contacts as possible to reduce the parasitic resistance. Okay? But we can make it, this is not so bad, but it is not the best. Let's go forward. Because in this way, we try to solve the problem for huge resistance. But in reality, how much W it is, how much L it is questionable. Okay? It means W and L both are not accurate. For example, why? Okay, from here to there, the length is the width of the polygate. Got it? But if you have a look at from this to the other side, sorry for that. It is not the same. Okay? Here we call it L. And there it is square root of 2 by L. Got it? So overall, what is the real L? Don't ask me. I have no idea. Okay? That is what I say. The width, the length are not accurate at all. Okay? Yeah, after such kind of layout, your EDA tool will help you to extract the equivalent W and L. That's it. But what is the problem? After extraction, so, the W is not what I think. So you need to redo the layout. It is too troublesome. Okay? Anyway, after such kind of layout for humankind, you can only estimate the W and the L, but without too much accuracy. Alright? So I wouldn't like you to be trapped in such kind of trouble. So I still wouldn't like to recommend you to do such kind of layout. But what else we can do? That is the simplest one. I would like to recommend you stacked layout. Okay? With such kind of stacked layout, we have a lot of benefits to reduce the parasitic capacitance by overlapping. While I'm telling overlapping, allow me to show you this. One finger, the other finger overlapped in this region. Okay, before overlap, you can see, I have sidewall, right? Sidewalls with large capacitance, right? But with overlapping, with stacked layout, the inner one, here and there, actually we reduce the parasitic capacitance very much. Got it? That's it. All right, so we reduce. Okay, how much you can reduce? Briefly speaking, 50%. Okay? Why? You can see. Oh, I told you already. Where will be the parasitic capacitance? 3 side walls and the bottom plate. Right? By overlapping, we share the same bottom plate for both transistors. So the bottom plate is reduced by 50. Okay? And how about the side wall? For each one, you have 3, right? But after overlapping, we have only 2 small, shared by 2 transistors. Got it? And how about the long walls? Finished. Got it? So, to be more precise, the parasitic capacitance is less than 50%. Congratulations. Got it? That's it. All right? And this is what I would like to share with you. For example, I told you already, M means multiple. How many fingers for this transistor you would like to have for layout? M equals 4. Means what? 4 segments overlapped all together, just like this. So keep this in mind. I told you already. For your H-spice model, you need to specify the W, the L, the M, blah, 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 for your transistor, right? When you write down M equals 4, automatically, you need to know, it means you segment the transistor into 4 pieces, then overlapped, stacked the layout for those 4 fingers. Okay, you need to think about this. When you write down M equals 4, the real meaning, just like this. Okay, don't tell me, oh, the final transistor is 4W by L. Don't shit me. Never. Okay, actually it is W by L, then 4 connected in parallel. They are stacked. But why? To reduce the parasitic. That's it. All right? We can go further. Even further. Till now, I only show you to stack the layout for your own fingers. Right? Just like this, I cut the transistor into 4 pieces, then overlap, stack the layout for all of them. So all those 4 fingers belong to the same transistor. Till now, from the beginning, we are only talking about this kind of stack layout, but we can go further. We can stack the layout for different transistors to make the overall layout even better. What is better? Again, reduce the layout area and parasitic capacitance. Okay? Allow me to show you a great concept about stacked layout, not for a single transistor, no, for multiple transistors. The main purpose, again, is to reduce the layout area and also reduce the parasitic capacitance to speed up the operation. And also for such kind of stack layout, from the beginning I told you already, it will be much less sensitive to implantation tilt. Alright, just like this. I told you already. During ion implantation, in this way, it will penetrate, it will penetrate too much into the substrate. It doesn't make any sense. So we need to tilt it just like this one in theory, but in practice, actually that. Okay? You can change the direction of your ion implantation, but equivalently, we tilt the wafer. Okay? That's it. So that is the way we try to do. But in this way, I told you already, the source, this area and that area, if it goes in this direction, the side diffusion here will be much larger than there. It means what? Your source and drain will never be exactly the same. They are not symmetrical at all. Got it? But for your simulation, it is supposed that source and drain are symmetrical. Right? So how to solve such kind of difference between the layout and your post or presim? You need to do such kind of stack layout. Alright? With even fingers. I warn you already. Even fingers to balance both areas. to balance source and drain. Okay, let's go further. This paper belongs to maybe IEEE transactions on electronic devices. Yeah, they are published by device guys instead of IC designers. Right, but their lives are much easier than us. Yeah, for some of the authors, for the authors of this paper, maybe from National Jiao Tong University, maybe, to my memory, yeah, they would like to see what is the impact of stacked layout. So you can see with such kind of very simple idea, I don't know whether or not they did the measurement or they only did simulation. Don't ask me, I have no idea. You can go back to read the paper. Anyway, with such kind of very simple idea, they would like to verify. Which layout will be better. So from the very beginning, yeah, it has a very wide transistor. Yeah, 40 microns. Then cut it into 2 pieces, 4 pieces, 8 pieces, then connect them in parallel. It means stack the layout. That's it. Okay? So according to the maximum operation frequency, you can see who get the most. This is for 40, 20, 10, and 5. Okay? That's it. So which one is better? 5. Right? Each finger. 5 microns. But you can see the tendency here. From 40 to 20. Very good. A huge improvement. From 20 to 10. Also very good. But from 10 to 5, not so much. Right? So if you go further, I promise you, it never be improved further. No. It will be worsened. Okay? Okay? You cannot do it again, and again. No, it has some kind of limits. But what is the limit? Okay. You can see, for a very long one, you cut it into half, it looks like this, right? You cut it further, it looks like that, right? My recommendation is, after it reach close to square layout, good enough. Don't go further. If you go further, you cut it again, and it will become this, right? Right? What is the consequence? Okay, if you go back here, if you cut it, you will generate this side and that side. The short side walls will expose, right? Then you need to get velocity for them. All right. So briefly speaking, for the final layout, if it is close to a square, good enough. Don't go further. Got it? Yeah. 我对你讲，你那个切一刀，有无？哦。What you can save? You stack both areas. So this and that will be overlapped with each other. So the parasitic for this and that will become 0, right? But you cut it, it means what? You will generate 2 short side walls, 2 bit. Something like this, okay? All that. So you increase the parasitic to the short side walls, but you only reduce the parasitic here or there for the long side wall. 你一刀砍断把两个拼在一起，所以这个长边跟那个长边会叠在一起不见了。不过被你一刀砍下来，所有的短边通通会跑出来，你就无赚到啥。 Okay, that's what I would like to recommend. Yeah, anyway, that is for your reference. Don't go further. Okay? They are lucky with such kind of very simple idea. With simulation or at the most measurement, they can publish full papers. Their lives are much easier than us. Okay, allow me to show you the procedure for stack layout. I mean, for multiple transistors instead of single one. All right. How can you stack the layout for many of the transistors? We hope they have the same width. Okay? If you go back here, you can see only for all those, they have the same width. Because I need to cover your long side wall, you need to cover mine. Okay? So, according to the width of the segments, we need to be exactly the same. But how about the length? Here or there? They can be smaller, they can be shorter or longer. Who cares? Got it? Yeah, so let's go further. They need to, for each segment to be stacked, they need to be with the same width, but possibly with different lengths. Okay, and this is the procedure. But allow me to explain instead of read the procedure for you. 用講較版哈，用講較緊，用睇較版。Okay, before I show you the procedure to stack the layout for many of the transistors, allow me to have such kind of explanation for stick representation. That is the real layout. Alright? But to simplify the procedure, I would like to only have sticks, 小小一根一根的棒子, to replace this one because it is too complicated to draw, to plot. Okay, so for each stick here means one finger of the transistor. Got it? And then I would like to share for each transistor with multiple segments how to stack them. For example, this is one of the transistor. 举一个当例子. Alright? So you can see if it has 4 segments stacked together, just like this, instead of that, too complicated to draw. Okay? 这太麻烦了。小歹话，咱用一支一支的锤下就好啊。Just like this. They are exactly the same in practice. Okay? And then, I would like to tell you, for such kind of one-stroke drawing, 一笔画, that is really important. Okay? If you begin from drain, right, with even segments, one to the other side. One means one layout. So you go from drain to source. 2, you just counted 1, drain to source. 2, source back to drain. 3, 4, blah, blah, blah. So you just use your finger from drain, right? Allow me to show you this. Okay, let's go. 1 and 2 and 3 and 4. Congratulations. With 4 segments, you go back to the same node. Got it? Got it? However, if you have only... what's this? Oh, okay, yeah. Odd number of segments. What will be the consequence? Again, from drain, right? 1, 2, 3. After 3 segments or odd number of segments to be stacked, the node will go from this to the other side. If you start from source 1, 2, 3, after layout, it will go to drain. Got it? That is the key point for such kind of one-stroke drawing. All right, keep this in mind. With even segment of the same transistor, with the even segments to be stacked, you start from drain, will also end at drain at the same node. Start from source will also end at source. Okay. However, for our segments, start from source will become drain. From drain will become source. You go to the other side of the transistor. That is what I would like to warn you, to tell you. Okay? Then we can go further. Oh, okay. That is only a joke. Forget about it. See? If we have 3 transistors, M1, M2, M3, with the same W, maybe different lengths, okay? That is what I mentioned. Can we stack the layout for them? Yes. Why? Because you have only one segment, one segment, one segment. So for the layout, I start from node 1, okay? 1, 1 means odd. Odd means from this side to the other side. Got it? 你要把它叠在一起的时候，对同一颗电晶体，如果你是偶数个叠在一起，那你又回到原点；奇数个你会到对岸，哦，跟那个林正义一样。OK，That's it。OK， 啊，林毅夫啦，不好意思，那叫林毅夫。Anyway。So for one segment, for those 3 transistors to be stacked, piece of cake, 1. Okay? If you are curious, let's go further. Right now, M1 is doubled. Alright, it means what? I have 2 fingers. The others has only 1. And as I mentioned, if you start from this node, M1 has 2 fingers, right? So you have 1, 2. Oh, sorry for that. You cannot connect M2 and M3, right? But we are intelligent humankind. You can start from this node. So 1, 2. Go back to the same node. Then 1. Congratulations. We stack all of them. When I say 1, 2, it means what? 2 segments. I say 1, 2, right? 2 segments of M1 are laid out. 我嘴巴喊1、2， M1 就生了2根 finger 出来，叠在一起。And then 1 for M2, the other one for M3. Got it? So that is the procedure for stack layout. We call it one-stroke drawing. 一笔画. Alright? In this way, we can go further for even more complicated one. For example, 3. Everybody has 3 segments. Right? So how can you stack the layout for all of them? The easiest one is this. Again, start from here. 1 and 2 and 3. All 3 segments are laid out. Then 1, 2, 3. 3 segments for M2 stacked. Then finally 1, 2, 3. Got it? But we can make it better than this. For example, you can have 1, 1, 1, 2, 2, 2, 3, 3, 3. Got it? All of them also stacked but with more dispersion, 散度. Got it? So according to the golden rules for common centroid layout, this is not the best. Actually, what I told you will be better or even much better than this. Okay? You can see no dispersion at all. 没有散度哈，没甲加这几会啦哈，没甲参这去。The other issue is this is the centroid for M1, centroid for M2, centroid for M3. They are far away. They are not overlapped. Okay, no common centroid. So with what I told you, 1, 1, 1, 2, 2, 2, 3, 3, 3. I promise you, they don't have, even though they don't have common centroid, but their centroids are much closer than this. OK， 所以这个layout一做出来，它的重心会非常的接近，虽然没有重叠远比这个家伙还要好。OK， that's it. All right, you can do it by yourself. Piece of cake with one stroke drawing. Okay, so for the other example, 2, 2, 4. What you can do? 2, 2, 4. Okay. To make it the best, okay, I start from here. 2 to 4 divide by 2. It means 1, 1, 2. I try to make common centroid for you. That is my recommendation. If possible, you divide the fingers by 2. Then do the one stroke drawing for the first half, then reverse it for the second half. I promise you, it will become common centroid. Got it? 你把所有的那个 fingers 的数目除以2，先画一半，倒着再画另外一半，倒过来画另外一半，它一定同中心。Okay, allow me to show you this crazy idea, but crazy but very good idea. 50%. For one stroke drawing, and for the other 50, reverse the drawing. You will achieve common centroid layout. Okay? So allow me to show you this. 2, 2, 4, right? So 50% means 1, 1, 2. 1, 1, 2. I start from the largest. Okay? That is the second recommendation. The largest to both sides. But right now only 50%, right? So allow me to show you this. Pay attention. 1 and 2. Then 1 and 1. 50%, right? Then go back in reverse direction. 1, 1. Oh, sorry. All right. Allow me to reward. 1 and 2. Then 1, 1. Go back. 2 and 2. Then 3, 4. Bingo. That's it. When I say 1, 2, or 3, I mean the number of the segments for each transistor. So allow me to tell you again. 1, 2 for M3, 1 for M2, the other one for M1, then 2 for M1, 2 for M2, then 3 and 4 for M3. Okay? And I promise you, they have common centroid, just like this one. 2 M3 here, 2 M3 there, right? M2, M1, M1, M2. All of them has the centroid here in the center. Congratulations. That is what I can help you. Okay? You can go even further. Hey, if I have 4, 2, 4, no worries, the same. 2, 1, 2. Divided by 2, right? 2, 1, 2. Do it by yourself. We have a break here. Okay? When I go back, I hope all of you already know how to do the layout with one-stroke drawing for first 50%. And after that, reverse the layout for the second half to compose common central layout by yourself.